Hello, my name is Grace Park, and I'll be presenting my project on the topic on the smallest n-1 gon containing a convex n-gon. Let's suppose that our goal is to construct a minimum area triangle barrier around a given convex object. If the object is a circle, we may try to construct an isosceles right-angled triangle. In this case, the ratio between the triangle and the circle is 1.85. I can reduce this ratio by constructing an equilateral triangle, as it gives the ratio of 1.65. Thus, it can be shown that the optimal construction is the equilateral triangle. However, if the object to be surrounded is a unit square, then the ratio between the area enclosed by any triangular barrier and the square is no less than 2. One can reach this bound in many different ways. However, even the best construction leads to a triangle whose area is twice the area of the square. It is actually known that the square is the most inefficient shape in regard to the triangular enclosure. This theorem has been proved by Gross, Egglestone, and Chakarian. They prove that every unit area convex shape K is contained in a triangle of an area at most 2. This theorem ultimately leads to my main problem. What are the analogous statements if I replace the word triangle with quadrilateral, pentagon, or hexagon? So let's take a few examples to understand what the situation is. Now, our goal is to construct a minimum area 4-sided barrier around a given convex object. First, if the object is a circle, the optimal quadrilateral enclosure is a square, and the ratio is 1.273. Next, if the object is a regular hexagon, the optimal quadrilateral enclosure is a parallelogram, and the ratio is 1.333. And most importantly, if the object is a regular pentagon, the minimum area quadrilateral enclosure is a trapezoid, and the ratio is 1.341. As you can see, the regular pentagon is the most difficult to enclose among these three. In general, the following result of Chakarian guarantees that every unit area convex shape K is contained in a quadrilateral of an area no greater than square root 2. As you can remember from the previous slide, there's a gap between 3 over square root 5 and square root 2. Then it is reasonable to ask the following question. What is the extremal convex shape with respect to quadrilateral enclosures? Kuperberg conjectured that every unit area convex shape is contained in a quadrilateral of an area no greater than 3 over square root 5. This problem is still open, but I made some progress by narrowing down the conjecture and proving the following theorem. Every unit area convex pentagon is contained in a quadrilateral of an area no greater than 3 over square root 5. In other words, I proved that the regular pentagon is the least efficient among all pentagons, while Kuperberg conjectured that the regular pentagon is the least efficient among all convex shape. So this is the distinction between my result and Kuperberg's conjecture. In order to prove this theorem, the main tool I used was the outer product of vectors. For any two vectors u and v, the outer product uv represents the side area of the parallelogram formed by the vectors u and v. The sign is positive if the counterclockwise angle between u and v is less than 180 degrees, and the sign is negative otherwise. Here's some properties of the outer product that I used: skew symmetry, linearity, and non-degeneracy. So here's the main idea behind our proof. Given a convex pentagon ABCDE, I first assumed that DEA is the smallest area triangle among all triangles determined by 3 consecutive vertices. Next, through E, I draw a line GF that is parallel to the diagonal AD. This produces a quadrilateral BCFG, which contains the initial pentagon. After extensive experimentation with GeoGebra, I observed that the ratio between the area of BCFG and that of ABCDE is always smaller than 1.342. It looks plausible that this construction always leads to a quadrilateral whose area is no greater than 3 over square root 5 times the area of the pentagon. But I still need to prove this rigorously. So the basic setup of our method is as follows. I start with a convex pentagon ABCDE, with DEA being the minimum area triangle. Then I draw diagonals AC and BD and denote the intersection of these lines as point O. I also denote vector ODSU and OASV. After an eventual scaling, I assume that the outer product of U and B is 1. Next, I define vectors O, BO, and CO as AU and BV as they are collinear with U and V. Here, A and B are two positive parameters which will play an important role in the sequel. After that, I compute the vectors AB, BC, and CD in terms of U, D, and B. I will now denote the vector OE as W and write it as a linear combination of vectors U and V. This introduces two more variables, C and D, which are also positive by the convexity of ABCDE. Finally, I construct FG parallel to AD, which creates the quadrilateral BCFG. Now I have to prove that the ratio between the area of BCFG and the area of ABCDE is smaller or equal to 3/5. The benefit of our approach is that I'm able at this juncture to express the areas of the quadrilateral and the pentagon in terms of the four previously introduced variables, A, B, C, and D. As you can see, the area of the quadrilateral is the area of the pentagon plus the areas of the two additional triangles formed in the corners. Moreover, the assumption that DEA is the smallest triangle gives us four inequalities listed here. It is also straightforward to show that ABCDE is a regular pentagon if and only if A and B equals √5 minus 1/2, which is the golden ratio, and C and D equals 1. After clearing out the denominators and simplifying the equation, proving our question is equivalent to the following. I have to show that the four-variable polynomial G is always non-negative, subject to the constraints obtained from the assumption that DEA is the smallest area triangle. This is a complicated problem, but I can circumvent it by writing G as a sum of non-negative terms. More specifically, I want to express G as a sum where every single term is a product of non-negative powers of A, B, C, D, E, F, 1 minus C, 1 minus D, A minus phi squared, and B minus phi squared with non-negative integer coefficients. Here, phi is the golden ratio, and E and F stands for the two more complicated expressions from the set of four inequalities listed earlier. I used the symbolic computer algebra system called Maple to look for such a solution. I eventually managed to write the polynomial G as a sum of 17 non-negative terms, as shown. Note that all coefficients of these terms are positive. For example, the first term's coefficient is 60 minus 26√5, which is approximately 1.862. Also, I can easily check that G equals 0 only when A and B equals 5 and C and D equals 1. Thus, the regular pentagon is the unique extremal pentagon with respect to quadrilateral enclosures. Another optimal result that I proved is that every unit area convex hexagon is contained in a pentagon of an area no greater than 7/6. There are numerous ways to enclose a regular hexagon within an optimal area pentagon, and the figure shows two ways of doing so. I can either extend two sides until they meet one another, or I could draw a line through a vertex until it intersects the intersection of two opposite sides of the hexagon. Despite the fact that this problem requires 6 parameters instead of 4, this proof is easier than the proof for a quadrilateral containing a pentagon. And this is because I do not have any rational constants like √5 in this situation. For further research, I hope to prove the following conjecture. For all n greater than or equal to 6, the ratio between a convex n-gon and a surrounding n-1 gon is 1 plus tangent 2 pi over n over n times cosine pi over n. The following figure shows 3 cases when n equals 6, 7, and 8. We have confirmed that this conjecture is true when n equals 6. However, further research is needed to prove the conjecture for all n greater than or equal to 6. If we use the outer product technique that we used for n equals 5 and 6, it requires 2n minus 6 parameters. So as the value of n increases, the number of parameters will also increase, which shows that we cannot use this technique for larger n values. Thus, a new technique is needed to prove this conjecture. These are selected references for the project, and thank you for listening.